now to take us into some of these deeper dive talks that Julie highlighted, I'm going to turn it over to my colleague, Sarah Mastroni, Program Officer at Ocean Visions.
Hi, everyone. Good morning. It's wonderful to be here with all of you. As Dave said, I'm Sarah Mastroni. I'm a program officer at Ocean Visions, and I'm very excited to transition us into our first deep dive here. So I'm going to introduce our next speaker, and she's going to take us on an exploration of marine energy and the landscape and potential ways that renewables can contribute to decarbonization. So, Dr. Andrea Copping is a senior research scientist at Pacific Northwest National Laboratory. She earned a PhD in Biological Oceanography from the University of Washington and holds the position of Distinguished Faculty Fellow at the University of Washington. Her research focuses on environmental effects from the development of wave and tidal energy and offshore wind installations. Andrea leads OES-Environmental, an international project on environmental effects of marine energy development around the world, as well as the research and development program for the use of marine energy devices to power blue economy applications. Dr. Copping is an associate editor of Coastal Management Journal and on the editorial board for International Marine Energy Journal. All right, without further ado, Dr. Copping, take it away.
Thanks, Sarah. Thanks so much. Okay, how do I know how to get this up? Resume presentation. No? Next presentation. That sounds right. Oh, okay. All right. Wonderful. I trust. I think I'm still on the previous one.
So, next session.
Duh. Terrific. Thanks so much.
Next, backwards.
Great. Super. Okay. Well, good morning, everyone. I'm very pleased to be here. As Sarah said, my name is Andrea Copping, and I am an oceanographer by training. Oh, get near the mic. Sorry. Hello. Oh my, that's a great start, isn't it? Andrea Copping, I was trained as an oceanographer, but I have been working in marine energy for the last decade and more. But I come to this as an oceanographer interested in the oceans, whereas most of my colleagues are engineers that came from the energy side. So very much my approach is, what is this doing for the oceans and to the oceans? I have worked in marine energy for the last 13 or 14 years, largely trying to understand environmental effects that might occur as we develop these machines and their systems offshore, the moorings, the anchors, the actual operation. And this has been a fairly new field. The literature was really thin back when I started. It's a lot better now, but there is still a lot to be learned. And what I'm going to do today is I'm going to take you on a quick little journey through what is marine energy, what is its place in the renewable energy portfolios, why would we bother to develop this, and then dive into some of the uses that are unique to marine energy, and finally conclude talking a little bit about understanding potential environmental effects of marine energy. I thought I had this figured out. Is that the next slide? No? Oh, that one. There we go. Okay, so what is marine energy? Now, Julie, who gave a fantastic talk, and others talked a little bit about offshore wind. That's not what I'm talking about. Marine energy is that which is harvested from the movement of ocean water, waves, tides, persistent ocean currents, but also large rivers we count in there, but also the differentials in the oceans for thermal differences throughout the ocean water and also salinity. And we use different technologies to harvest energy for each of these types of movement of water. What we see on the three on the left and also the one on top, the core power, these are different means of harvesting wave power. You see they all look a little bit different. And this is because waves are very, very difficult. Stand on the shore of the ocean and you see waves coming at you from different directions, different periods, different amplitudes. So far, each of these technologies There's different companies developing very different types. There are some that even sit on the sea bottom as the wave passes over with a pressure differential. That picture in the middle with the two big round things, ocean perpetual motion, is been designed. They're very large turbines that are supposed to go in the Gulf Stream for the persistent ocean currents, large turbines that turn slowly. The bottom middle one, NOVA, and the two on the right are technologies used to harvest tidal energy. Largely, they look like turbines that we're kind of used to. We put these same kinds of things in the rivers. There's been very little technology convergence in this field so far. Everybody knows what wind turbines on land look like. They're all those three-bladed upwind turbines. That hasn't happened in this field. It probably will eventually, at least 2 or 3 wave devices, a tidal device, etc. But it's still very early in the development, the deployment, and the operation of these devices. So why would we develop marine energy? Well, it's clearly one more low carbon energy generation system that can help with climate mitigation. Purely and simply, that's what we're here about, is trying to understand how we cut these carbon emissions. Now, if the world were in fact to go to 100% renewables, it's estimated that about 80% of that demand could be taken care of with wind and solar. But what about the other 20%? That's where marine energy fits. And it fits very well in some very specific places. So this allows countries to add yet another option to that renewable energy portfolio, those that are looking like the US is, of all of the above as alternatives to fossil fuels. And again, place yourself at the edge of the oceans and you know what a huge resource it is. The crashing waves, the fast moving water and tidal races, and then the persistent currents. That map in the lower right was created by colleagues at another national lab, the National Renewable Energy Center, and it gives a snapshot of the kinds of energy resources we have in the oceans just in the US. That sort of bright blue indicates the wave energy resources, and you'll see it's really concentrated in the Pacific, along the west coast, Alaska, Hawaii, the South Pacific Islands, a little bit on the east coast. The orange are tidal resources. There are only a few really large tidal resources in the US, Cook Inlet in Alaska, Puget Sound in Washington State, and coastal Maine. But there's many smaller tidal resources in most of the estuaries around the country that could be tapped. And then we get to the persistent ocean currents. And those of you that remember your basic oceanography, you know that currents become very intensified on the western side of ocean basins. That's our east coast. And the Gulf Stream comes quite close to Florida and to North Carolina, where there are research efforts and development efforts to tap that current. Never mind the day after tomorrow, we do not believe that this is going to actually melt the world down. And then we have thermal gradients, those differentials in the ocean, obviously in the tropics with warm tropical water on top, cold ocean water below. That's largely the Caribbean, Pacific Islands, and Hawaii. And we have the potential for salinity current power also at the mouths of rivers. These are all viable. They are all under development in one form or another. And that's just the US resources. Many other countries have really wonderful resources as well. But early on, the US Department of Energy, whom I work with, was the major funder of this kind of work. And they were concentrating very much on grid scale power. That which keeps the lights on, the air conditioning going. But it became clear a few years ago that marine energy might be better suited, have a unique role in something smaller. This initiative they've called Powering the Blue Economy, to look at all these end uses where power may actually be worth more. Some electrons cost more money than others. If you're far out at sea and there aren't other sources, it's pretty important to have a way to power things. There are some unique locations where marine energy has a real advantage. For instance, in high latitudes where solar energy doesn't do well in the winter and wind turbines don't do very well in those harsh conditions. Also, remote coastal communities and islands, imagine native villages in Alaska or Caribbean islands. They are all dependent on diesel for electricity. We also have the opportunity to generate power and use it at sea for ocean observations, which I'll spend a little time talking about, and also offshore aquaculture. We all know we need to grow more fish. and shellfish, but aquaculture is moving offshore really around the world, and this is to avoid competition with other uses and also some of the detrimental environmental effects. But as these farms go further offshore and get bigger, they need power. The option is to take diesel gensets to sea, or perhaps use marine power generated on site. We also have emerging markets. Marine carbon dioxide removal that I want to address next is one that marine power, maybe marine energy, may be perfectly suited to. We're also very interested in whether we can recharge underwater vehicles, especially large AUVs and vehicles of that sort. So let's talk about marine energy and marine carbon dioxide removal a little bit. Several of the previous speakers touched on this, and there's just a few examples here. We know there are various electrochemical approaches being pioneered in the laboratory and in small areas, and all of them need substantial power. Where are we going to get that? Can we co-locate these MCDR processes, plants, if you will, offshore with marine energy? It seems like a very good possibility, and there are some tidal power resources being explored for this right now. If we're going to grow massive amounts of macroalgae, seaweed, we don't need power for the growth portion, but we certainly need it for nursery sites, for harvesting, for transporting and processing. And if we choose to sequester that carbon at depth, we need to be able to sink it. All of this requires power. And this is being pioneered in a number of places around the world in small ways. It obviously is very tightly tied to offshore aquaculture. But it appears that this is a really good possibility, and we have several research programs across the Department of Energy portfolio that are focused on this. Artificial upwelling and downwelling, bringing deep, rich, nutrient water up to the surface to increase productivity, especially in tropical areas. This has not really been explored to a great extent yet. We don't understand the power requirements, but we know they will be substantial. And there's a real possibility in tropical areas that ocean thermal energy conversion, or OTEC, focused on those temperature differentials in the ocean, is a possibility. And finally, we need to monitor what we're doing as we move forward with MCDR programs. We need to know if we are actually attaining what we want in effectiveness, but we also need to really understand if what we're doing is carbon negative. There's a lot of processes and many enthusiastic projects being planned around the world, but we really have no idea how effective they'll be. This can, of course, requires the development of new sensors. Perhaps they can be ganged up with other existing ocean observation systems, but we need to really understand what they are, and all that requires power. And the ARPA-E, which is the DARPA for energy within the Department of Energy, the sort of moonshot, high-risk organization, has been examining this potential for a period of time now. My laboratory is working with NOAA's Pacific Marine Environmental Laboratory. They on the sensor side, us on the marine energy side. So these are the kinds of things where marine energy can have this unique role with MCDR. So I want to talk a little bit about community energy. Marine energy is probably well suited for remote island communities and islands. These communities depend on diesel being flown in or barged in. This is very expensive. It is not secure. You may not get your delivery before the ice sets in, as has happened in Alaska in the past. And obviously, you increase chances of spills, air contamination, human health problems, and everything else about putting more carbon in the ocean. If we were to locate marine energy off these many coastal areas, we'd need to have a little bit of energy storage, a little bit of a microgrid associated with it, but this can significantly increase the energy resilience and the community resilience of these small communities. There's several programs the Department of Energy is working on to provide technical assistance of this sort. The ETIP program, which I can never get, Energy Transition something program, allows communities around the US to apply for this kind of help. We also are examining whether we can locate idle-ready marine energy devices, small ones, onshore of vulnerable communities so they can be deployed and operated following disasters. We know we can supply small amounts of power to hospitals and also to first responders. Along with the power, there's other co-benefits. Desalinating seawater, again, very important in a disaster. And we have shown you can use wave energy to desalinate seawater. You don't even need electricity, you just use the mechanical motion of the wave devices. Seawater air conditioning, using cool water to pump through buildings and residences so you don't use electricity. There are experiments underway to look at beach nourishment and enhancement of coral reef growth. Again, you need some power to do this, and marine energy is being looked at for that. And it's a really interesting use around the world, examining whether you can put marine energy devices offshore to dampen storm surge and large waves for coastal defenses. Throughout this, of course, it's absolutely essential that we think about what the communities want. What are their values? What are their concerns about competition with existing uses and environmental concerns? And programs that are moving forward are very much trying to take this into account. Okay, now I want to talk a little bit about another use, and that's ocean observations. This has been a big thing around our laboratory and with our partners. My colleagues and I surveyed a large number of ocean observation professionals in the sciences, security, and industrial uses. We asked them how much power they use for their platforms, whether they're fixed or mobile platforms, what they do with them, where they work, and what would they do with them if they had more power. We all know that these assets at sea are run on battery power, which means you send a ship out to refresh and change the batteries, or you bring the assets back to shore. What if we could keep them out there longer? And this graph here on the y-axis, you're seeing the different classes of ocean observations, mobile and fixed assets, and on the y-axis that was, and on the x-axis is the amount of power. And what's interesting is, except for a couple of uses, most of that power requirement is less than 10 watts needed at a time. This is very, very doable, so we're looking at these small generators. The ones that require more include HF, high-frequency radar, which is often placed on coasts in very isolated areas and often without a power source. And this is used for search and rescue, it's used for weather prediction. And then repowering these very large underwater vehicles takes quite a bit of power too. So we're still working on how we'd actually deliver that. We've worked with a whole different series of ocean observation platforms. Why are we working with this community specifically? I think this group here probably has a good sense of it. The general public wonders. This is a $7 billion a year industry worldwide. So it's a significant use of power. Use of money and probably power. We've worked with weather buoys, NOAA's weather buoys, the DART system, which is the tsunami early warning system, with various profilers like the Argo floats, which both the Argo floats and sensors we put in the Arctic, we don't get them back. They are very, very energy effective. They last quite a long time, but then they sink to the depths of the ocean. Can we elongate their lives? Can we provide better outcomes? When we asked these ocean observation experts what they would do with more power, they talked about longer missions, extended time at sea, extended life for their sensors, and also adding additional sensors, particularly to collect more biogeographic and chemical data in the oceans. Okay, I want to just mention one of the really emerging marine energy sources, and that is ocean thermal energy conversion, or OTEC. This is very old technology. It's been around 50 years. It's pumps and pipes and heat exchangers and turbines. Nothing fancy as it is in some of these newer devices. Why don't we see many of them deployed around the world? Because they're very, very capital intensive. But we think we're starting to have a breakthrough in some other countries, island nations, but also here in the US with the present climate for climate. Seawater air conditioning is very much tied to this, that you can use cool water to bring into houses and buildings. And thanks to the thermohaline circulation throughout the oceans, you can actually do seawater air conditioning a lot more places than just the tropics. For OTEC, you require a 20 degree centigrade differential, top warm surface water to cold deep water, but that's not true for seawater air conditioning. So we're starting to see this really take hold in temperate climates and even up into Scandinavia and so on. That last little drawing down on the lower left is a project my group is just starting out on, where we're looking at multi-use purposes for an OTEC platform. Once we bring up all this cold water, we can use it for power, for seawater air conditioning, so-called district cooling. But what about enhancing aquaculture with some of this nutrient water? What about producing hydrogen and ammonia as transportable fuels that eventually, hopefully, can be used for shipping? These are the kinds of things that we're investigating at this point, really kind of the early part of it. Okay, the last thing I want to address here is environmental effects of marine energy, which has been a lot of my bread and butter for quite some time. I do work with this OES-Environmental. I represent them for the US in this international consortium of 16 nations. And we examine potential environmental effects through what we call a stressor receptor framework. Stressors are any part of the system, the device itself, the mooring, the anchor, the installation, the cable, the electrical cable, and we break it down to really understand which receptors, and that is, the stressors are those parts of those devices that could cause stress, injury, or death. The receptors are the animals, the habitats, the ocean processes. And we break these down for each individual type of device so we really understand where those pinch points are, with the idea that we can help, we do set research agendas, we help get those seminal research projects funded, and we also collate and disseminate that information so it's very transparent and very available worldwide. Some of these things we've made great progress in. We have a very good understanding of what the underwater noise of these devices are and how it may or may not upset marine mammals or fish. We understand the electromagnetic fields. The collision risk is one of the really tough ones. Will animals run into rotating blades of turbines? No good analog, no good, and very difficult observationally. So there's still a great many things we need to do. But we're caught in a strange catch-22. We need more devices in the water in order to do more work and understand better, but we're really being slowed by permitting processes worldwide because of uncertainties of this sort. Regulators and stakeholders are very concerned, and it's sometimes difficult to get regulators in certain countries to accept results from other countries, and I very much include this country in that. Okay, so I just want to wrap up here. I hope I've convinced you that marine energy can be a useful solution in the decarbonizing of the oceans, both for just creating power, but in the short run especially, providing power to remote communities and using power at sea for ocean observations, offshore energy. But also, this may very well turn out to be the best energy source for running our marine carbon dioxide removal processes. So as representing a U.S. Department of Energy National Lab, we work very closely with other labs, we work with universities, and we work closely with the marine energy industry. And I want to tell you that there is a real commitment to being enduring partners in this desire to rebalance the carbon climate in the oceans. So I'd like to thank you, answer any questions.
Thank you so much. That was a wonderful talk. So we're going to move into a bit of a Q&A now. So if anyone has a question, I'll try and run around. Yes. So let's see. I think this one's good.
All right.
Okay.
I can't see, so.
Thank you. Great talk. Really glad to hear about this. A question that's been haunting me for many years here, with ocean energy, how far is the curve between here and price parity with, say, land-based renewables?
It's a great question, and I glossed over that with the early efforts being to try to look at grid scale for marine energy, and it was the levelized cost of energy that's made that very difficult. Offshore wind curve is dropping really fast, and it's going to get down to where solar and onshore wind is reasonably soon. Marine energy is much more expensive. I think anyone who's worked in the oceans and put devices in and expecting them to last understands this. So this is why we have moved, at least initially, into this powering the blue economy, these smaller uses. Let's face it, if you can provide power at sea, every electron is worth a great deal more. If you are shipping diesel into a remote Alaska community, it costs a lot. So that's why we're really trying to de-risk these devices and really get forward to those same kind of price points. But there has to be a pretty multi-layered strategy to get there. Great question, thank you.
Other questions? Yep.
Thank you for the talk. It was extremely interesting. I wonder, and this may be an open question, is it known how much energy we can draw from the ocean before we would have some localized effects on currents, eddies, and ecology?
Another great question. I work with a whole series of hydrodynamic modelers, physical oceanographers who are using very high performance models looking at, for example, we start in tidal areas, which are usually basins or bays, and look at how much energy can be extracted before you start to get some breakdown. And it turns out it's tens to hundreds to thousands of turbines before you get that kind of breakdown in an enclosed tidal area. No one will ever let you put that many in the ocean for other reasons. So we feel pretty good there. Wave energy is the same. There was great concern early on from the surfing community because you will in fact decrease wave height, but you decrease it perhaps in terms of millimeters. And as far as the large ocean basins, things like the Gulf Stream, the jury is still out, but the early some of us are a little skeptical on the ocean current ones, to be honest, not because we're going to slow the oceans, but because we think we could end up just moving the currents a little bit and losing out on our actual generation. So the bottom line is we think we would have a very, very hard time having much effect. But it is these high performance models that allow us to look at this. And the same is true for OTEC, by the way.
Move on to one more question. We're just going to
yeah.
take one more from our online participants.
Great.
Hello. Oh, there we go. Okay, question from the online participants. What are your top 5 wish list items for partnership opportunities?
Great question. We really looked at, in terms of, because of who I work for, they talk about markets and applications. We are extremely interested in continuing in the ocean observation space because we think that's really a place we can make a difference, going further, faster, deeper. I think offshore aquaculture is a really important one, and this is opportunities for true co-development. As new types of aquaculture come online, we'd like to develop with them. We are very interested in decarbonizing shipping. This is a very, very heavy lift, but starting with electrifying of ferries, which is happening. We have some wonderful experiments going on in the Orkney Islands, north of Scotland, where they are using hydrogen from excess tidal and also wind energy, trucking it over to the main island and using it on their ferry systems. So that's a really big start right there. That's 3. Let's see. I think the marine carbon dioxide, we are very committed to being there. Probably the best use of marine energy there, first off, is in this monitoring space, ensuring that we have good sensors that can be powered appropriately. And a 5th one, let's see. Probably the remote communities. That one should have been higher. We think that there's real possibilities to make a difference in people's lives. We have some very cool examples out of some of the dry islands off in the Arabian Sea off India, where they put in a small OTEC plant that also desalinated seawater. And in the space of 3 years, they saw incredible improvements in public health. They had electricity, they had air conditioning, and they had clean water. These are the things that can make a difference in people's lives while we're decarbonizing. Okay.
Thank you so much. Let's get another round of applause for Dr. Copping. And if you have more questions that you didn't get a chance to ask, feel free to find Dr. Copping at breaks and lunch and, keep the conversation going. So I'm going to turn it over to Dr. Millicent Pitts for our next deep dive. Thank you.